So what are conjugate acids and conjugate bases? Okay. If you say if you look at the chemical formula, yes, but I want to explain this in a more technical level. So let me go ahead and use one good example that we will see again and again. Ammonia is a base, okay? It reacts with water to become NH4 plus and OH minus. Okay. Now there's a little story about these acids and bases, and I can include this over here. But we'll go deep next year again. But when we talk about acid and bases, we have two definitions that we use in the AP curriculum. We have the Arrhenius acids. Bronsted-Lowry, yes. So we have the Arrhenius definition, and we have the Bronsted-Lowry. Okay. And the way I like to exaggerate these two definitions is that Arrhenius is the little racist kind. Not Arrhenius is racist. Arrhenius is actually a very cool scientist. He is actually the person who coined the term greenhouse gas for CO2 that I didn't know until I bought a chemistry book and I read about it. So the definition, I want to exaggerate it, and I call it a little racist. It's kind of labeling. If a chemical is capable of if the chemical has H plus, that shall be called an acid. If a chemical has a hydroxide ion, that shall be called the base. And we have a little dilemma right here, and that's the ammonia right there up top. Well, if you look at ammonia, it doesn't have OH minus. And how we call it a base. So it is a base based on the Bronsted-Lowry definition, because for Bronsted-Lowry, it's more of a equal opportunity employer, that it does not care about who you are, where you come from, but what you can do. So if you can produce H plus, is an acid. If you can produce OH minus, it's a base. But how do we describe this production? So we simply say, well, for an acid to produce, right, it's actually called a proton donor. Okay, you can produce it, right? So we can give away the proton, the H plus. That's an acid. Acid. So it's basically the same thing as Arrhenius. If you can accept, if you can accept H plus, acceptor or receiver, either way. Okay, if you can accept a proton, like what we see up there in the equation, NH3, and accepting one proton from H2O. Okay, so that's why we call it a base. So let's go ahead and label these, okay, real quick. So we would call the ammonia a base because you can see from here to here, it is clearly taking in a proton. And for the water, it is clearly a acid. And I want to, yes, it's donating a proton. And I must add one thing here. Acid and base, it's about the job role. We are not saying water is acidic. No. It's just what is in the equation. Yes, it's just a role they place in the equation. Water plays the role of an acid. It's giving away a proton. So water's conjugate base would be H3O plus. Hold on. Let's see here. Let's finish this, and then you will see the answer. Now, and there's another reason why I use use ammonia, because it's a weak base, and I can use the double-headed arrow. So now, look at the product side. They can go back to the left. So to go from ammonium ion back to ammonia, what has to happen? And so it's an acid, and to avoid confusion, let's call it a conjugate acid.
So water's conjugate base is OH minus.
And when you say water's conjugate base, that it is a very loaded question, because when you say, oh, what's water's conjugate base? That statement implies that the water initially is playing the role as an acid. So that's how you know, oh, water is playing the role as an acid, so it gives away a proton to give rise to the OH minus. So that's how you label the acids, and you have to write out the equations. Water is going to be very important for all the equation writing in the second semester. So just a little bit of foreshadowing of what comes your way next year. It'll be very exciting to do all these acid-based calculations.